Our next presenter is András Károly. You can see from the title of his thing, Hunting, Exploiting Bugs in Kernel Drivers. He was one of the first experts in the world who got the Offensive Security Exploitation Expert Certificate. He's also a member of the Gulyás team, Gulyás or Goulash, I don't know how exactly wrote it, representing Europe together with Predators at the Cyber Olympics finals in Miami. He's going to have a few more words about himself, so take it away.
Yeah. Welcome everybody, nice to see you here. Yes, as you heard, I will talk about kernel driver exploitation. So I'm András Károly, and just some words about myself. I work for Deloitte Hungary as a manager for the security and privacy group. Previously I had also some IT security job. I have more than 10 years experience in IT security in several fields of the security. And I am member of the Gulyás, the Hungarian Gulyás team, and so on. So basically I'm a technical guy, I think. Today we will exploit kernel drivers. Why exploiting kernel drivers is interesting nowadays? Because it is more increasing popular compared to previous years. This is because of the fact that there are a lot of vulnerable driver what is used on computers. There are several drivers shipped by the operating system itself, but there are a lot of third-party drivers. You can find bugs that can be exploited, and with a successful exploitation you can compromise the whole system, because if you are in kernel land, then you can do whatever you want. If you are in kernel land, then our main goal is to run our shellcode, but there are differences between the user mode shellcodes and the kernel mode shellcode. So basically we just evaluate our privileges, and after that we run our well-known shellcodes. During this presentation I will focus on Windows 32-bit kernel drivers, but the basic and the background is the same for the 64-bit operating system also. Before you step into the kernel land, you had to know some background about the differences between the user mode and the kernel mode. There are rings, ring 3 and ring 0, the user mode and the kernel mode. These rings are basically different access levels to resources. These rings are implemented by the operating system, but usually enforced by the hardware itself. Windows only use 2 rings, so one for the kernel mode and one for the user mode. From user mode, the application has limited capabilities. The application or the process is not able to connect or to communicate directly with the hardware. The application itself has separated environment for each process, and because of this fact, it is relatively hard to manipulate the background system or even crash the background system. However, in kernel land, you have all the possibilities. You have full access for everything, the kernel code itself, the memory for the kernel, the hardwares, and for everything. And because of this, it is enough to take a small mistake and you will crash the system. Nowadays, drivers in Windows are WDM drivers, Windows driver models. That is exactly a framework for device drivers. And the name is device drivers. It isn't means that these drivers has to take care about any kind of driver part of the computer or connected to the computer. So try to imagine that there is an application, for example, an antivirus or firewall, and it installs a driver to the Windows, a device driver actually, to provide kernel mode functions to the user mode application. These WDM drivers was introduced with Windows 98 and 2000 to replace the previous used VXD. To develop this driver and drivers, And to understand it, you have to use the WDK. It's provided by the Microsoft. It includes a lot of tools, documentation, samples, so it is a must-have tool for everyone. The most important thing for us is that these drivers are communicate with the I/O request packets. We will use that later. The basic of the communication is the following. When the driver loaded into the kernel mode, it will create a driver object with the I/O create device function. This object will describe the whole driver, and it will include major function pointers for different functions. From these pointers, we will take care about the device control function, because this function will be handle all of the IOCTL calls. So every IOCTL call will land it to this function. After this, the driver register a symbolic link for the device, what it creates, and this symbolic link will be used by the application from userland. So a user mode application will be able to open the device and access to the device through this symbolic link. The IRP packet includes IOCTL code. IOCTL code actually describes a lot of things. For example, the device type, the function code, transfer type, required access. But the most important thing is the IOCTL targets a function in the kernel driver. So if we try to call a function in a kernel driver, then we should target it with the correct IOCTL code. There are generally three transfer types for these IOCTLs. This is just the MSD and description for these. Usually the buffered IO and the neither method is used. Yes, that is neither buffered nor direct I/O, but in short, just is method neither. The main differences between these two methods is that in case of buffered I/O, there is a I/O manager in kernelland that handle all of the buffer magic. So when the application call the driver with the IOCTL call, then the I/O manager will grab the buffer from the user space, copy to the kernel space, and when the driver finish, it will copy back the result to the user mode buffer. While, on the other hand, the neither method is different, because application usually use this method to provide complex structures to the drivers. So in this case, the whole buffer itself and pointers to the buffers are directly passed to the driver. So to communicate with the driver, you should use some Windows API function. For first, you have to open the symbolic link with create file. And after that, if you receive a handle for that, then you can use device I/O control for IOCTL calls. And if the driver implement, then you can use write file and read file to pass stream data to the driver. The device I/O control needs some, is it recognizable? Okay. The device I/O control needs some parameter, and the most important for us is the I/O control code, the buffer, input buffer pointer, and the size, and the same for the output buffer. In some case, especially in method neither, we will play with this pointer I will talk about later. To identify the target, you should use some tools that is publicly and freely available from the internet. The two main tools that is available, the WinObject, it's part of the sysinternals tools, and the driver view. With these tools, you can identify the loaded drivers, the base address for the drivers, access levels, and some other important information that can be used for later. There is another tool, the IRP tracker, that is very useful if you don't want to reverse engineering the whole driver, but you would like to understand what kind of communication it uses. With this tool, you can capture the IRP packets, and you can see a detailed view on the IRP. So from this view, you can export the IOCTL codes, you can recognize the buffer size and so on. So it is very useful. Bug hunting in drivers, of course, if you have source code, then use it. That's the most important, but usually we don't have, so we had to use some reverse engineering. IDA, I think, is a de facto program that we use in this case. So you have to understand and read assembly well. But for general bug hunting, you can use some fuzzers. There are IOCTL-BF and IOCTL fuzzer, also Kartoffel, that are very useful for basic fuzzing, and they are able to identify the general problems very fast. For example, method nadir mode, the transfer type of the IOCTL, cause pointer manipulation possibility, and these fuzzers are able to change the values for the output buffer, and maybe if the driver doesn't check the output buffer position correctly, then you will be able to overwrite kernel space memory with the output buffer. Of course, you can use kernel debugging, and as I mentioned, the device object contains a lot of important functions and function pointers, but from those we should set our first breakpoint on the device control. So why we love method nadir? This is what I mentioned before. There is a direct parameter passing from the application, from the user space to the kernel space. So sometimes the programmer just doesn't correctly handle these parameters and make the necessary checks on them, so it can be used for arbitrary memory overwrite. And with this, you will be able to achieve code execution in kernel space, or you will be able to modify some important kernel structures. So with this, it is possible sometimes to escalate your privileges just with one IOCTL call. This is write what-where exploitations when you are able to write something to somewhere. This exploitation method is not only limited to the method nadir transfer type, but there are some logical error in the application where you can use the same methodology. But sometimes there is limitation on your flow because the what is sometimes limited. So maybe in size or in value it is limited. You can see some example on this. Maybe you have control on EAX register and the ECX, but it is only 4-byte overwriting. So you have to take care and make sure that what kind of memory will you overwrite and with which kind of data. Sometimes there is only increasing or decreasing on the variable pointed by the register, and maybe it will be also enough for us to achieve code execution. There is no standard process for this write what-where exploitation. You have to reverse and understand the whole environment for the process, but you have a lot of opportunity for these. There are some interesting targets for the write what-where exploitation. However, I have to make a note that on modern Windows operating systems, especially on 64-bit operating system, there is a new protection on kernel level, the KPP, it's kernel patch protection, and this KPP routine is take care about the modification of the descriptor table and the dispatch table also. But it isn't able to recognize, for example, local function pointer overrides in the vulnerable kernel driver. So it is still important target for us. When you can trigger a code execution, then you have to know the followings. What are the different between the user mode code execution and kernel mode code execution. So because the program flow comes from the kernel mode, the code we will run in a kernel space. That means the standard user mode shellcodes will not work there because there is no kernel 32 standard Windows API because that is a user mode API. So it is possible to build a custom shellcode that is only works in kernel mode, but is not so comfortable. So usually we change the way and we try to build a shellcode that is staged. It means, for first, we would like to try, for example, evaluate our privileges, the attacker privileges, in kernel space. And if we finish with this, then we would like to give back the flow to the kernel to return to the attacker process, to the elevated process. And from that point, we will be able to run our user mode shellcode, but with higher privileges. This privilege escalation usually happens with token stealing. These tokens are security descriptors of a process, so a system knows security properties and access levels and everything related to a process with this token. We are able to find a key thread or e-thread structure at the kernel space that is related to the current process with the FS register pointed 124 offset. From there and from this structure, we are able to identify the e-process structure, and the e-process contains several interesting variables that can be used to find a system process. And if we find a system process, then we can steal its token, and we will be able to replace our process token to the system token. How it works. So here is a K-thread structure. We can see that here you can find a pointer to the K process. K process is a part of the E process structure. It's just the first. But after that, there is a unique process ID. In modern Windows operating system, if it is 4, that it means that the analyzed structure is related to a system process. So we compare it to 4. But if it isn't 4, then we have an opportunity to walk through the e-process list with the active process linked list. So we have a forward link here, and we can use it. If we achieve to identify a system process, then we can use its token and the token address and replace our attacker token with this system token. You will see a working assembly code in my demo later. For debugging, because you know the basic backgrounds for the kernel exploitation, it is just very quick overview because we have short time, but we should jump into the demo. For debugging, you have to set up 2 machines because you are working in kernel land. It means if you set up a breakpoint and pause or break the machine in kernel, that the whole system will stop. So you can use the same. You can't use the same machine as a debugger and a debuggee. You have the chance to set up 2 physical machines, but you can use virtualization also. In my case, I use 2 virtual machines because I have Linux on my host machine, so I have a Windows in virtual machine to use debugger function, and I have a Windows debugging machine also in virtual. In virtual machine scenario, you can use virtual serial ports to connect the machines. You have to also enable remote kernel debugging on Windows system. Bootini is not existing nowadays. Instead of that, there is boot config data editor, the bcdedit, and you can use these settings to enable it and set up the settings. Of course, it could change based on your needs. And we should switch to the demo. So we have here a target machine, and there is the two tools what I mentioned. The driver view, it is very useful just to walk through the loaded drivers and identify some functions on them. We have a vulnerable Windows driver here. It's for the demo purposes. There is another tool, the WinObject. It is very useful also to gather almost the same information, and it is important to check the access levels. Because we are in a limited user environment, we have to make sure that everyone has read and write permission on the device. So we have it, it will be okay. We know here is a reverse disassembled code of the driver. I don't want to walk through the driver entry and other functions, but we'll have closer look on the vulnerable function. Here you can see there is a buffer at the dump driver function, and here you can find function pointers. It seems it is an array of function pointers, some other variable there. Here you can see the code set up the function pointer array. It stores function pointers for different functions. Later on, it makes a short check, a probe for read is generally used in kernel drivers to check that is the kernel have access to the pointed memory, and is it mapped just to prevent crash. So it makes a short check on the input buffer, and if everything is correct, then it will simply copy the buffer content to the local buffer. We can identify here that there is no length check on the buffer, so we can be sure that at least there is one buffer overflow identified here. We can't just pass a slot buffer as we would like to send, because there is stack cookie checking in all of the modern drivers, so it is default nowadays. But as we can see, the function pointers are stored after the buffer, so maybe we will be able to write through our buffer and override the function pointers. And if we walk through, then we can identify that here something interesting happened. So it will call a dynamically function based on a variable comes from the buffer. We will see it in practice how it's works. So we switch for the Windows debugger. You can use the driver object function to identify the target driver. As I mentioned, the device control major function is important for us, so we will put a breakpoint on them. Let it run. Switch back to the target machine. I don't need these tools yet. And I have a proof of concept code here that doesn't trigger the vulnerability but communicate with the driver. So for first, we have to set up the correct IOCTR code that the driver implements. We have to use symbolic name for the driver. We can open the driver with the device IO control function, as I mentioned, and with the create file function, and we can send IOCTR codes to the driver with the device IO control function. Here we set up input buffer. It is 40 bytes with big A's, and we set up an output buffer. In this example, the output buffer isn't used, but it doesn't matter. I just simply let it run. The machine stopped. So I switch back here, breakpoint hit, and we just start to walk through the commands. Here you can see that from the IRP packet, it catch up the IOCTR code and compare to the value. If the IOCTR code match to this, then it will serve this. If it doesn't match, then it will jump over and exit from the function. We just jump into the function. Here you can see some other stack preparing. And we hit the vulnerable code. Here you can see that the function pointers will be stored and set up on the stack. The stack is changing at the bottom. Here is a probe for read. Sorry, I made a reload because it seems it lost the symbols. If you have symbol files, that is very useful because when you are debugging the kernel itself, then you can see the resolved names for the variables, for the function calls, or whatever else, and it can be very useful and makes your job easier. Yeah, that's good. So, yes, it is resolved now. Here you can see that it is a probe for read call. We don't care about that. And here, EAX register points to our target buffer. So it is in kernel space. Here you can see that there are the 4 prepared function pointer in a function pointer array, and we will just call the memory copy function. If we again check the EAX register pointed memory area, then you can identify that it was filled up with our buffer. So from here, we are able to plan our next steps. Maybe we would like to increase our input buffer size with 4 and manipulate these last 4 bytes to point to our shellcode. So we will need to prepare our kernel mode shellcode, and we will have to manipulate these 4 bytes. But if we walk through on the following code, then we can identify that here is magic key check. That's very funny, but usually it happens in production drivers also. So it just checks for a value on the stack, and if it doesn't found, then it just jump over. So I let it run, and I switch for the working exploit, and I try to explain the differences. As you see, previously we just used 40 bytes input buffer. Now we prepare it in the following way. Because it checks the magic key at the first 4 byte position, we place it at the right place. After that, from the reversed code, we can identify that it will call a function pointer based on the second 4 bytes, so based on the second D word on the buffer, just after the magic key. So it will be an offset for the function pointer arrays. So if we if we set up this variable to 0, then it will call the first stored function pointer. That is actually what we will try to overwrite. So I set it up to 0. After that, I fill up the following buffer space, but because I increased the buffer size with 4, on the last 4 bytes, I just put the address to our shellcode. But where is our shellcode? Here. It is just a hex representation of the kernel mode shellcode. You will see it in the debugger in assembly. and I get the shellcode address with the ID function, but because it is just a reference for the variable object in Python, I have to add 20 bytes for that address, and the data actually start from that address. So this is how we can put our shellcode address here. And what is funny, Python will allocate the memory for the variable executable by default. So we can use it directly to jump into the shellcode and let it run. So this shellcode is the token stealing shellcode. And it will elevate our privileges with the token stealing method. And after that, I will just simply run a new cmd.exe. And if everything going well, then we'll achieve higher privileges. So let it run. I just make sure that our breakpoints are set up. Yep. So I let it run and trigger the vulnerable IOCTL, and it stopped. We hit the breakpoint. Here is the major function from the device IO control. It is just some basic check, and here we will jump into the handler, some preparation on the buffer, and call the vulnerable dump_drv function. For here, you can see at the bottom of the stack, at this window, it set up the function pointers. Here is the probe for it, it doesn't matter now. And EAX is the target of the memory copy. So if we check the memory range around EAX, then we can identify that here are the 4 function pointers. Here is the starting memory for the copy. And if I let it run and check again the memory range, then our function pointer, the first function pointer, was overwritten with our manipulated address. And if everything is going well, then if I disassemble comments on this address, then this is actually how our shellcode will start. Yes, you can see here. So we can walk through. There is a magic key check here. But because we prepared our buffer well, then we will pass this check. So we will not jump over. We just hit here the vulnerable function call. And because of the second D word was 0, then because of this calculation, we will call the first function pointer. So if I step in to this code, then you can see we just achieved a code execution from kernel. And if you see this memory address, then you can recognize that this is not in kernel space, but in user space. So this is our kernel mode shellcode in user space, stored in the Python variable. So I just walked through it until I hit the first command, just store the variables for later restore, zero out EX, search for the key thread structure with FS register plus 124 offset. And from that structure, I extract the address of the E process structure. I stored it in ECX because it is our attacker E-process structure. I walk through the active process link and search for another one with the linked list. From then, I identify the base address of the eProcess structure. I have to subtract the same value, what is the offset from the eProcess beginning to the forward link. I compare the unique process ID variable for 4. It is something different. That means it isn't a system process. If it is not a system process, then I will jump forward to the next eProcess structure and compare that unique process ID to 4. As you can see, now the second analyzed eProcess structure related to a system process. That means it is okay for us, and we should check its system token. And so because it is pointed at this offset in the east process structure, I just save it on EDX. And because on the first sum row, I stored our attacker process E process structure in ECX, then with this command, we can just simply replace our attacker token, security token, with the system process token. So we just simply elevated our privileges with this. I restored variables with pop-id and return into the kernel mode. From this moment, the kernel knows that from this moment, if the kernel check any access restrictions or any security properties on our attacker process, then it will think that it is a system process, so it will give all the rights for everything. Because we are again in kernel mode, I just simply let it run, and it will finish the IOCTL call and make the response. And if I switch back to the target machine, you can just realize that a new command prompt is started, and if I run a who am I, then you can see that it is anti-authority system now. So that is how privilege escalation works. This is a local privilege escalation attack. However, there are some kind of methodology to do it remotely. But remote kernel exploitation is very different and much harder compared to the local ones. From this, I would like to make some conclusion because we had very short time, and this is a huge amount of data what I would like to share. It was just an introduction, and this is really just tip of the iceberg, because there are a lot of possibilities to exploit, to achieve code execution, to modify kernel space structure, and so on. So there is a lot of research works on it. You should use Google. There are a lot of Black Hat conference talks on this. So it is not just 24 minutes topic. It is not magic, so if you have experience on standard exploitation techniques, then you just only have to know and understand the kernel mode structures and be familiar with that. And after that, it is just simple, like in user mode. And because of the fact that these kernel drivers are usually vulnerable, and there are a lot of third-party drivers. Actually, Windows drivers are become more and more secure nowadays, but a lot of third-party drivers, just think about antivirus drivers, for example, are vulnerable for any kind of attack targeted by IOCTL calls. It can be good targets, so you should focus on that and do some research, and it can, I don't know, if you have code execution on a target machine with a penetration testing on or whatever, with a limited environment, then if you are familiar with these techniques, you can prepare your own environment and find these bugs on the same environment, and you can be sure that you will be able to escalate your privileges and compromise the whole system. So it is very good to play with that. That was all what I would like to introduce during this presentation. Thank you for your attention. And maybe if you have a question, then I will be here around, so just catch me and ask. Thank you.